You ever stop and think about how your body can just switch gears? I mean, one minute you're in a flat-out sprint to catch a bus, and the next you're settling into a nice steady jog. It all comes down to this incredible internal energy economy. So how on earth does our body manage all that? Let's get into it.
All right, so here's our game plan. We're going to start with that burn you feel when you're working out hard. Then we'll see how our body cleverly recycles its own waste. After that, we'll check out how it taps into different fuel sources, and we'll wrap it all up at the central hub where all these metabolic roads meet.
Okay, first up, let's talk about that intense, burning feeling. You know the one. It's the feeling that tells you you are really pushing it.
Oh yeah, we've all been there, right? Your muscles are just screaming at you and you get that unmistakable burn. Well, that's not just some random feeling. It's a very specific signal that your body has flipped a switch and gone into emergency power mode. So what is actually happening down at the cellular level? So this really lays it all out. Our bodies have two main energy strategies. On one side, you've got your default mode, aerobic metabolism. It uses oxygen, it's incredibly efficient, and you can keep it going for a long, long time. But when you sprint, you need energy way faster than your lungs can supply oxygen. And that's when your body flips over to anaerobic metabolism. It's super fast, yeah, but it's also kind of messy, and there's no way you can keep it up for long.
And that backup plan? It's called lactate fermentation. It's basically the body's way of getting a quick hit of energy without needing any oxygen. You can think of it like the cell's version of hitting the nitrous button in a race car. It's a critical fix for a short-term energy crisis.
And the star of this whole process is a molecule called lactate. Now, for years, lactate got a really bad rap. Everyone blamed it for muscle soreness. But we now know it's so much more than just a waste product. It's actually a temporary fuel that lets your muscles keep firing on all cylinders, even when they're totally starved for oxygen.
Okay, so that fast and messy backup plan is great, but it does create a bit of a problem. If too much lactate builds up, it can get dangerous. But of course, our body has this incredibly elegant solution for both cleanup and recycling.
Right. Here's the catch. While lactate fermentation is a total lifesaver for a quick burst, letting it pile up in your bloodstream starts to lower your blood's pH. That condition is called acidosis, and it's seriously bad news. It can mess with how your cells work if it goes unchecked. And this is where the body's teamwork is just amazing. Your muscles, after working so hard, just dump that lactate into your blood. Your circulatory system acts like a high-speed courier, whisking it away to the liver. And what does the liver do? Well, it performs a little bit of biochemical magic, turning that lactate right back into glucose, the very fuel your muscles, and especially your brain, need to function.
But this recycling thing, it's not as simple as just hitting the rewind button. No, it's a really clever and pretty energy-intensive pathway.
This whole process of making new glucose is called gluconeogenesis. It literally means new glucose creation, and it is absolutely vital. I mean, when you're fasting or you've just burned through all your available sugar, gluconeogenesis is the thing that keeps your brain from shutting down by feeding it a steady supply of fuel.
Yeah, a good way to think about it is like this. Glycolysis, the process of breaking down sugar, is like the main energy highway going downhill. It releases energy. Gluconeogenesis is trying to go back up that same highway, but some of the on-ramps are one way. You can't just go in reverse. You have to find a special detour.
So these one-way ramps are three specific chemical reactions in glycolysis that are basically irreversible because they release so much energy. To get around these roadblocks, gluconeogenesis uses its own special set of enzymes to create these bypasses. It's just a brilliant biochemical workaround that lets the body rebuild glucose from scratch.
But this recycling program, it isn't free. In fact, it's really expensive, metabolically speaking. It costs the liver 6 high-energy molecules just to turn 2 lactate molecules back into a single molecule of glucose. This huge cost is exactly why your body is so careful about when it runs this process. It only fires up this expensive factory when it absolutely has to.
So, what happens during those longer, less intense efforts? Like a marathon, when your glucose is running low and you can't just keep making more? Well, the body shifts gears again. It starts to tap into its largest and most powerful energy reserve, fat.
So, the process for burning fat is called beta oxidation, and here's the play-by-play. First, a fatty acid gets activated. Then, it gets shuttled into the cell's power plants, the mitochondria. Once inside, it goes through this 4-step cycle that just chops off 2 carbon units, one after another, releasing a ton of energy carriers with each slice. The cycle just keeps repeating, chopping up that long fatty acid chain piece by piece. And this right here, this is the payoff. I mean, just look at that difference. A single molecule of glucose gives you about 32 units of ATP, our cell's energy currency. But a standard 16-carbon fatty acid, that gives you a staggering 106 ATP. It's not even close. This is why fat is such an unbelievably good fuel for endurance.
All right, we've talked about burning sugar fast, recycling lactate back into sugar, and then burning fat for the long haul. Let's bring it all together now and see how all these different roads connect at one critical central hub.
If there's one molecule you remember from all of this, let it be acetyl-CoA. Because in the world of our metabolism, it's pretty much true. All roads lead here.
So, what is acetyl-CoA? Well, it's that 2-carbon unit we saw getting sliced off of fat molecules. It's also what glucose gets broken down into when there's plenty of oxygen around. Its main job is to carry those carbon atoms into the final stage of energy production, the Krebs cycle, which is where the vast majority of our cellular energy gets made.
Probably the best way to think about it is like a universal token for the cell's main power plant. It doesn't matter where the fuel came from, whether it was sugar, fat, or even protein. It has to be converted into this acetyl-CoA token before it can get into the main furnace and generate massive amounts of power.
And here's where you can see it all just click into place. Whether you start with carbs or fats or even that lactate that got recycled from your big sprint, all of those breakdown pathways funnel down to produce acetyl-CoA. It's the grand meeting point of our entire energy economy.
So, let's do a super quick recap. Lactate fermentation gives us that fast, oxygen-free energy, and its main output is lactate. Gluconeogenesis is that expensive but crucial process of making new glucose, and beta-oxidation is that super efficient cycle that breaks down fat into our central hub molecule, acetyl-CoA.
When you step back and look at it, this whole system is just this beautiful, intricate dance of supply and demand, of recycling and efficiency. It lets us adapt to pretty much any physical challenge we throw at ourselves. It really makes you appreciate the insane complexity that's happening inside us with every single step we take. Which of course leaves us with one final, pretty important question. What happens when this elegant, finely tuned machine breaks down?